Okay, it's time to get started. So let's settle in. All happy to be back from the weekend, but all right. In case you guys thought I was done promoting pre-health societies, I'm not. So there's a few more today. This one is the Aspiring American Medical Professionals. They meet on Thursday this week. I'm assuming that non-Americans are welcome, but it's not obvious from the name of the organization. But they have some information here. There's also the PPASA. I believe that's the Pre-Physician's Assistant, is what PPA stands for, and then SA is some other part of that name. But they will meet also, I guess, tonight, accepting new members. We're going to do Physician's Assistant as your future career. And then Alpha Eta Alpha, I believe they are a sort of a general purpose pre-health society for all majors and all types of health professions. They will be meeting also on the 30th, which I guess is Wednesday, after class that day. So again, a lot of options for you if you want to check those out. All the information will be in the notes, and you can get in touch with those respective organizations. So what we're going to continue on with today is more of things related to electronic structure. Now we're talking about how electrons are arranged in atoms. This is kind of the whole big topic of Chapter 2. Chapter 2 is kind of a beast, as you might have figured out from looking at it if you've read the book. So we're going to take our time going through it. It usually works better if only one person talks at a time. So we could try that for now, okay? All right, so the Chapter 2 has a lot of different things involved. It's a pretty deep chapter, a lot of different topics. So we're going to spend still the rest of this week going through that, and even probably the first part of next week. So there's lots of things left to do in that. But what we talked about at the end of last time was the Bohr model, which was sort of one of the earlier quantum models, if you will, or quantized models, I guess, for the atom, which was said that you have the nucleus at the center, you have these circular orbits that the electron follows as it goes around the nucleus, and that each of these orbits represents a different energy level, and they are designated by simple integers, what we call quantum numbers. Now we're going to get some more details of that today. So as we kind of established last time, each of these circular orbits represents a different energy level, and photons are absorbed or emitted as electrons move between the energy levels. Today we're going to start talking about that a little bit more quantitatively and giving you the equations that are associated with those energy levels, as well as how we use them in different contexts. So the Bohr equation, as it is often called, is that one of these atomic energy levels, the energy is given by this constant here, minus 2.18 times 10 to the minus 18 joules. And so that's the sort of Bohr constant. I don't think that's on your periodic table. You have to remember that number, but you're going to use it a lot. And then the other part of the equation is just z squared over n squared. So we drew a qualitative energy level diagram last time showing that the energy levels get closer and closer together as you go to higher and higher values of n, and that's because of this 1 over n squared dependence that we have on that quantum number n. And what we also notice is that there's this minus sign out front, and so what this means is that, and this is a pretty typical physics and chemistry convention, you have a positively charged nucleus, you have a negatively charged electron, so that energy that they're interacting with is going to be conventionally given as a negative number. Whenever you have an attractive force of interaction, you're going to have negative energy levels, is conventionally how it's done. And what we see is that this energy level, if you've taken pre-calculus, this hopefully makes a lot of sense mathematically, will go to 0 as n goes to infinity. So what that means is, remember, n going to infinity means we're taking the electron further and further away from the nucleus. As we get to really, really far away, there's no more energy of interaction, and it approaches 0. All right, so it's going to be kind of on that scale. And just to define these terms a little bit more clearly, z in this is the atomic number, which is defined exactly the same as we initially defined it, which is the number of protons in the nucleus. This z squared term is technically there, although I don't think you guys are really ever going to use it, because I'm pretty sure all the homework questions just deal with hydrogen, where z is 1. And so that term basically goes away because 1 squared is just 1. But if you had a system that had more than one proton in the nucleus, you would account for it with this z squared term. And then n is that quantum number that we defined last time. It's an integer number that designates what energy level you're in. Starts at 1, goes to 2, 3, 4, 5, and so on. Now this form of the equation up here, we're not really going to actually use a whole lot. The form of the equation we're going to see a lot is when we go between energy levels. So what's the change in energy as you go from one value of n to another, which is then of course related to either absorption or emission of a photon. So all we do for delta E, we've seen delta in one other context before. Delta just means final minus initial. So if you're comparing two different energy levels as the electron moves between them, we just take this equation up here and just subtract two different values of n. And so what you get then is minus 2.18 times 10 to the minus 18 joules, and then final minus initial. So you still have this z squared term, although again, as I said, we're not going to typically use that. The number of protons doesn't change as you move between energy levels, so z squared will still be a constant for that particular problem. But the important part of it is you have this here, 1 over, I'll abbreviate it as nf squared minus 1 over ni squared, where these are the two different values of energy of n, the two different quantum numbers that the electron is going between. So nf, as the abbreviation suggests, is the final n value. So this is where the electron ends up at the end of either absorbing or emitting a photon. And then ni is the initial, it's where it started. So if you're calculating delta E, it can be positive or negative. Positive meaning that the electron is going to a higher energy level and the final value of nf would be larger than ni, or the opposite can also happen where delta E is negative, you're going from a higher value of n to a lower value. So that comes out mathematically as long as you keep straight which one is your final and initial value of n. Alright, so that's the equation we'll use, and there's some other things that then come out of this before we start doing example problems with it. So one of them is, and one of the reasons why people thought that this equation was very interesting discovery and why it still has a lot of validity today is that it correctly predicts some things about the hydrogen atom. And one of the things that it correctly predicts is the ionization energy. We're going to talk about ionization energy at the end of this chapter, so we haven't seen it yet, but essentially ionization is just the amount of energy that it takes to remove an electron completely. So as we said, when you form a positive ion, you have to remove one or more electrons, and so ionization energy is the amount of energy it takes to completely rip that electron away from the nucleus. Okay, so that's the process we're referring to, and in the context of the Bohr equation, what that means is that ionization is the process where your final value of n goes to infinity. So that's again the situation where the electron has been completely taken away from the influence of the nucleus, and so if we use that equation then, so that again means electron completely removed is when n goes to infinity. Alright, so delta E is then minus 2.18 times 10 to the minus 18 joules. So the amount of energy required to remove an electron, we just use this equation. And if we're talking about starting with ground state hydrogen, so we have hydrogen initially in its lowest energy state, we want to figure out how much energy required to remove that electron, all we have to do is put in these two different values of infinity. Nf is infinity, the initial value being 1. And so what we get is minus 2.18 times 10 to the minus 18 joules times 1 over final value of n squared is 1 over infinity squared minus 1 over the initial value for starting in the ground state as we are here, 1 over 1 squared. Alright, and then those of you that have taken pre-calculus, which I think should be every one of you, and I don't remember if they covered this in pre-calculus because it's been so long and it wasn't even called pre-calculus when I took it. But anyway, they should have taught you what is, if you have 1 over infinity or 1 over infinity squared in this case, what value does that approach? 0. So this whole thing goes to 0. And what you're left with is just that constant but without the negative sign in front of it, 2.18 times 10 to the minus 18 joules. So this Bohr constant here, in addition to being a key part of this equation, also is the ionization energy of hydrogen, and it matches very well with the experimental values, so again, lending some validity to this model and to this equation. So we don't have to know that number, but it does show that this equation has some utility in calculating fundamental physical properties like ionization energy. But the way that we're going to primarily use it in this course is to calculate the wavelength of absorption or emission, or alternatively the frequency, which is related to the wavelength, as we know. And we kind of talked about this in concept, and the concept is that the energy of the photon, whether it be absorbed or emitted, is equal to the difference in the energy levels that the electron is going between. All right, now it's going to be technically the absolute value because photon energies can never be negative. You can't have a negative wavelength or a negative photon energy, but we know that delta E can be positive or negative. But that magnitude, that difference between the energy levels, is what dictates the energy of the photon that's absorbed or emitted. And so then if we want to find the wavelength of the photon, which again is equal to h over the frequency, that's given by hc over the absolute value of delta E. So in other words, when we do a lot of these Bohr equation problems with the Bohr model, what we're going to be doing is we're going to be using this Bohr equation to calculate delta E, and then we're going to relate that to either the wavelength or the frequency of the photon that's involved in that process. And keep in mind then, from this equation and from the concepts we talked about last time, if you have a positive delta E, that means you're absorbing a photon, and you're going from low n to higher n. In other words, Ni is smaller than Nf, and the opposite is true for emission. So if delta E is negative, that doesn't mean you have a negative photon energy. It just means that the change in energy for the electron is negative. That reflects emission of a photon. And the nice thing is, if you remember these concepts here, then I'm going to draw a box around because I think they're important. If you remember these concepts, you don't necessarily have to be paranoid about getting the equation right, because in this equation here, if you flip NF and NI, you're just going to change the sign if you get that wrong. You're not going to change the value that you get. So you can always look at the values of N that you're working with and figure out whether it's absorption or emission just by looking conceptually at those, not having to necessarily just rely on the equation all the time. So the point is, if you're calculating delta E, it's important to get the sign correct because that can be positive or negative. But if you're calculating wavelength or frequency, you just take the absolute value of delta E anyway. So if you flip your N values in the equation, it's not going to cause you to get it wrong necessarily. So it's always important to not just be robotically putting in numbers, but to always think about what they mean and what the expectation is. All right. One key point that's worth pointing out, we're going to circle back to later on when we talk about some of the limitations of the Bohr model, is that this equation, this delta E equation, or just the energy level equation that I started with, they only apply to one electron systems. Now, it has that z squared term in it. That reflects the number of protons, so it doesn't necessarily have to be a one proton system, but the equation does not work if you have anything more than one electron in your atom or your ion. So the one that we'll primarily do it for is hydrogen, which, as we should know by now, is the first element on the periodic table, has one proton and one electron. It would also work for select ions, which are not necessarily ones that we observe all the time in real life, but can be generated under some circumstances. So helium, which has two protons, if you take off one electron, that would be a one electron system. Lithium has three protons, so if you take off two electrons, you're left with only one more. Beryllium, 3+, and so on. So most of these, especially beyond these few small ones here, you can't really actually generate. You're not going to get iridium 76 plus or whatever it is. So like you're not, for the heavier atoms, you're never going to really see this. You're not going to put those in, you're not going to form one electron systems from those. But for some of the small ones, you can, and it's just worth bearing in mind that that equation means one electron system, but it can be more than one proton because of that z squared term. All right, so let's then look at some sample problems of how we're going to use these equations. So the first one is true or false. Minus 6.36 times 10 to the minus 19 joules is an allowed energy level for a lithium 2+ ion. Okay, so remember, one of the key concepts here with the Bohr model is that you don't have continuous energy levels. You have these energy levels that are given by the quantum number n that are spaced out by some amount, and those are the only allowed energy levels for that electron. So we want to know, is this particular one here allowed for a lithium 2+ ion? So in this case, we're not talking about going between two different energy levels. We're just talking about a stationary state or a single energy level that is starting at, and so we just want to know if that's allowed. So again, the equation that relates this is minus 2.18 times 10 to the minus 18 joules times z squared over n squared. So we need to know z for lithium. It's not hydrogen, so the z is not going to be 1. We go to the periodic table. We can find that always on the periodic table, so you don't have to memorize the order necessarily. Alright, so lithium is here. It's number 3, so that means lithium 2 plus has 3 protons. It also is a 1 electron system. We can verify that that's true also. So Z is equal to 3 for lithium. And so if we want to answer this question, is this an allowed energy level, we need to solve for what N would be. So what has to be true about N? What did we talk about last time? Can N be anything? It has to be, someone said small integer. It can be any integer, but yes, it has to be an integer. So if the value of N that we solve for is non-integer, that means this is a not allowed energy level. So only the ones that have integer values of N are allowed. So we're going to just use this equation and solve for N. So minus 6.36 times 10 to the minus 19 joules is our given value for E. And we're going to set that equal to minus 2.18 times 10 to the minus 18 joules. And then Z squared over N squared. So Z squared is 3 squared, or 9, and then we're solving for N. Alright. So we're going to do a little bit of algebra. So I'm going to, often in class, I'm going to shorten things by just putting it into the magic algebra machine, because I don't want to do all the steps on my own, because it takes time that we don't have. So anyway, with a little bit of algebra, we should find that when we rearrange, we do some cross multiplying and dividing and all that good stuff, we get N squared is equal to 30.85. Now hopefully we remember all of our squares and square roots. We don't even have to put this in a calculator, but if we did, we would find that N is equal to the square root of this number. And this is clearly not one of our integer square roots, so we get 5.55. So this is not an allowed energy level, so the answer to the true or false question is false, because N must be an integer for this to work. Alright, so that's one way we could use this equation, just to figure out which, whether this is an allowed value. But again, the more common ways are going to be talking about absorption and emission of photons. Alright, so let's do one here. We have determine the energy and wavelength of light emitted when hydrogen jumps from the second orbit to the ground state. Alright? Now, anytime we see a problem that's asking us about hydrogen atom, wavelength of a photon, absorbed or emitted, we should immediately think of the Bohr equation and write it down to figure out what we have and what we need. So again, it's always good to start with sort of the equation or the concept that relates to the problem we're doing, and then figure out what parameters we need to solve it. So it's Z squared and then 1 over NF squared minus 1 over NI squared. And when we plug in the numbers that we're given, so Z for hydrogen is 1, and all the rest of the problems we're going to do are going to be hydrogen, because that's, I think, all the ones you're going to have on your homework assignments and tests. So we're pretty much going to just ignore this parameter, or this term here, Z squared, because it's 1. 1 squared is just 1. But then we have to put in the values of N. In some cases, they're not given to you in very explicit terms, as is the case here. So when we say second orbit, that's a fancy way of saying N equals 2, and that's where it's starting from, so that's going to be our initial value of N is 2. And then we go to the ground state. Now, what value of N does the ground state refer to? Right, so whenever we see the word ground state, that means we're talking about N equals 1, so in this case, it's terminating, or the final value of N is going to be 1. Okay? So we have 2 and 1 are the two values of N, pretty much the simplest situation we can have. And we put these into this equation. So final value of N is 1. Initial value is 2, so it's 1 over 1 squared minus 1 over 2 squared. And the number we should get from that is minus 1.64 times 10 to the minus 18 joules. Now, as I said before, if we were calculating delta E, and if that was sort of our final answer we needed, we would stop here, and the sign being positive or negative would be very important. In this case, we're looking, though, for something about a photon, wavelength of light. So then we have to recognize that the energy of the photon, this is going to be an emitted photon because we're going from a higher to a lower value of N, so we're losing energy, and that energy is going to be given up as a photon. So the energy of the photon is just equal to the absolute value of that delta E, that difference in energy levels, or the positive 1.64 times 10 to the minus 18 joules. All right? Remember, photon energies are always positive, wavelengths and frequencies are always positive, so if If you get a negative sign for delta E, you just drop it out to get the energy of the photon. And then the equation that we need then is that the wavelength of the photon is equal to h times c over the energy. We introduced this equation last week as E equals hc over lambda, so we just solve for lambda in this case, and this is what we get. So h and c are those constants we're going to use a lot in this chapter, which are on your periodic table, so you don't need to know them. So it's 6.626 times 10 to the minus 34 joule seconds for h, 3 times 10 to the 8th meters per second for c, and then the energy of the photon is this number here, which will be in joules if it comes straight out of the Bohr equation, and we don't have to convert it to anything else. It's just that number put in directly to the equation. All right, and then so what we get is 1.21 times 10 to the minus 7 meters. We didn't specify the unit here, but again, the more conventional way to write this is in nanometers, so we would multiply this by 10 to the 9th and get 121 nanometers. All right. So again, I'm not going to show that step explicitly, but if we ask you to convert it, as we often will, to nanometers, that's what you would get. I guess it also wanted the energy of the photon, so this number here would also be part of the answer. That's the energy of the photon, which corresponds then to that wavelength. Okay, so the Bohr model is, we'll do a couple others, but it's really, in most cases, the identical process. Use the Bohr equation to find the difference in the energy levels, and then relate that to one of either the energy or either the wavelength or frequency of the photon using those photon equations that we learned last time also. All right, next one. Hydrogen undergoes a transition from n equals 3 to n equals 5. So we're talking about a different one here. Not necessarily, it doesn't have to start or end at the ground state. It can go in between energy levels that are not the ground state as well, which is the situation here. Is a photon emitted or absorbed during this process, and what is its frequency? So pretty much the same process as last time, except this time we're looking for frequency instead of wavelength. And we also have to answer the question, is it emitted or absorbed? Now to figure out if it's emitted or absorbed, we don't have to do any math. So we're going from n equals 3 to n equals 5. So we're going from low n to higher value of n, means that we're going to a higher value of the higher energy level, which means that the photon is absorbed. All right, so there will be some questions where identifying whether the photon is emitted or absorbed is part of the answer. It can be, either process, but if we know that the energy level is getting higher, if the electron is gaining energy, going to a higher value of n, that must mean it's absorbing a photon, it's taking in that energy from the photon. So we already know that the photon is absorbed, now we have to find its frequency. So we use the same Bohr equation. Minus 2.18 times 10 to the minus 18 joules, and then z is still 1 because it's hydrogen, so that z squared term doesn't matter. And then we just have to put the two values of n. So final value of n is 5. And again, at this point, if we mess it up, it'd be okay because we're just going to get the absolute value anyway, is what we need. But it's still good practice to put the values of n in the correct order, especially if we ask you about delta E, which we don't necessarily ask you about here. And what we get in this case, if I did my math right, is 1.55 times 10 to the minus 19 joules is our delta E. In this case, it should be a positive number because we're going from a lower to a higher value of n. So that number checks out if we write the values of n in the correct order. And then what we need here now is nu. So remember the equation E equals h nu, the simplest of the photon equations for energy, which means that nu is just going to be the energy of the photon divided by h. The energy of the photon would be equal to this delta E. The amount of energy absorbed from the photon has to be equal to the amount, the energy difference between the two levels. And so we just plug those in. 1.55 times 10 to the minus 19 joules. And then h is that same fundamental constant. So really almost identical process as last time, but just a different equation at the end to get frequency instead of wavelength. And so what I got was 2.34 times 10 to the 14 hertz. So that's the frequency, and it's going to be, again, to reiterate, an absorbed photon. So it'd be that frequency of photon being absorbed during this process. All right, so it's really, again, that same set of steps almost every time. Use the Bohr equation to find delta E, and then once you have delta E, you need to know what to do with that. Are we going to just use that number directly and be done, or are we going to convert that to an energy or a photon wavelength or frequency? All right, and then finally the last one. No, not the last one. Sorry, we have two more, but one of them is going to be a quick one. Just to really drive the point home, we have a lot of. We're a little bit ahead of the schedule, so we can do a few different examples to see all the different possible variations. So in this case, we're talking about the Paschen series. Paschen, it was named after the scientists that discovered it. A lot of the Paschen lines, as they're called, which are visible, so they were easy to observe. And these involve atomic transitions that terminate at the third energy level. So again, that means N final would be 3. And they start at, in this case we're talking about emission, so they're going to start at some higher value of N than that, 4 to 3, 5 to 3, 6 to 3, and so on. Any of those observed emission lines would be referred to as the Paschen series. You don't need to know that, but that's sort of the background for this problem. And a Paschen line for hydrogen is observed at 1094 nanometers. And we want to determine the level from which the transition originated. So here we're working backwards. So normally, in the last couple of problems, we found either the wavelength or the frequency. Here we're giving you the wavelength and frequency and asking you to find the level that it originated from. So in other words, what is the initial value of N? All right, that's our unknown in this case, is the initial value of N. So we're working backwards here, and what we should do first is recognize that this delta E from the Bohr equation, the absolute value of that is going to be equal to hc over lambda. So if we know the wavelength of the photon, or its frequency, whatever we're given here, we can find the delta E, because this is going to be hc over lambda is the energy of the photon, and then that energy of the photon is equal to the change in energy that the electron is undergoing during, in this case, the emission of the photon. So we plug in the numbers that were given. So hc, the same two constants, and then our given wavelength is 1094 nanometers. As we talked about last time, if you're using this equation, or really any equation in chemistry, you have to be careful about units. So C is in meters per second, so our wavelength needs to be in meters. So we have 1094 nanometers, and 1 meter is 10 to the 9th nanometers. So don't forget this conversion. And so what we get in standard scientific notation is 1.094 times 10 to the minus 6 meters. Again, in the visible, infrared, UV range that we're usually working with when we're talking about atomic transitions, your wavelengths will typically be on the order of 10 to the minus 6, 10 to the minus 7. That's the typical range we'll see. All right, so we put that number into here in the correct units now, 1.094 times 10 to the minus 6 meters. And that then gives us the energy of the photon, which is, of course, related to delta E. So what I got was 1.817 times 10 to the minus 19 joules. So that's the absolute value for delta E. If we're going to use the equation correctly, though, we have to recognize that we're talking about emission here. Which may not be obvious from the question. I probably could have worded it a little bit clearer, although there's a word there, so no mystery. It is atomic emissions. And that means our delta E is actually less than 0. So in reality, the real value for delta E, this is the energy of the photon, or the absolute value of delta E, would be the negative of that. Here it's a little bit important that we recognize this, because if we set up the equation with the values of N and we're solving for it, we have to make sure that we have the correct sign for delta E, or we'll get the wrong value for N. Alright, so again, delta E is negative because we're talking about emission of a photon, as is stated in the first sentence of the problem. This number here, which we get from the photon wavelength, is the absolute value of delta E, or it's the energy of the photon itself. Alright, so it's a negative delta E, and so then we just set up the Bohr equation. Delta E minus 1.817 times 10 to the minus 19 joules is equal to the Bohr constant, minus 2.18 times 10 to the minus 18. Z squared is just 1, so we leave that term out if we wish. And then our final value of N for the Paschen series, it terminates at 3, so that's going to be our NF is always going to be 3 for the Paschen series. And then what we're solving for, again, is the initial value of N. Where did that electron start when it relaxed to the third energy level and gave off this photon. Alright, so here we're solving for this. Algebra is a little bit more complicated than what we've seen so far, so make sure you practice if you're rusty on it. So again, I'm not going to go through the algebra typically in this course, except in rare extreme situations, but we do some algebra, and what we should get is that the initial value of n squared is equal to 36 when we solve for that, and that means if we take the square root of both sides, the final that value of n will be 6, which is an integer value. So if you do a problem like this where it's asking you to solve for the value of n, if you don't get an integer, you probably are almost 100% certainly messed up your math somewhere, okay? And that could come from, again, not having the right sign of delta E, or not having these in the right order corresponding to that sign of delta E. So make sure you're careful about that. This was, again, the most involved one, so save some time to look over that if there's things that don't make sense there. Now the last one we'll do is more of a comparative problem. So we want to know which requires a higher energy photon, moving from n equals 1 to n equals 3 in a hydrogen atom, so both these are absorption processes, or moving from n equals 2 to n equals 4 in a hydrogen atom. Now there are two ways to do this problem. As is often the case, there are multiple ways to approach one of these. We could just do this equation twice, calculate delta E for both of these situations, and figure out which one is larger. We have two pairs of NF and NI values. We'd have to do the calculation twice and then compare delta E. Perfectly valid way to do it. I have no problem if that's how you would choose to, but I think there is an even faster way, because if you remember last time, what we talked about is if we draw sort of a, this is still semi-quantitative energy level diagram. Remember, n equals 1 is at the bottom, then comes n equals 2, but they get closer and closer together as we go up. So n equals 3 is going to be closer, n equals 4 is going to be even closer. So in this case, I think it's a very straightforward comparison. If we're going from n equals 1 to n equals 3, we're going across this energy gap. And if the energy levels are getting closer and closer together, if we go two values of n starting at n equals 1 versus this transition here, n equals 2 to n equals 4, which one is clearly larger? Even if I didn't draw my diagram perfectly, I think it's obvious, right? So that's going to be a larger energy gap. So this problem here, we don't even necessarily have to do any math, because we can draw this qualitative diagram where the energy levels get closer and closer together as we go up, and it becomes pretty clear that anything that starts at n equals 1 and goes to n equals 3 is going to be a larger gap than going from 2 to 4. Alright? Some of the comparisons, might not be obvious, like is n equals 1 to n equals 3 going to be bigger or smaller than n equals 2 to n equals 5? In that case, in one situation we're going across 2 energy levels, another situation we're going across 3. So which one of those is bigger? Maybe not obvious. But in this case, we're skipping just one energy level each time. We're going between, two that are separated by two values of n. So the comparison is straightforward, and that must be a larger one because of this compression of energy levels as we go up. So that's going to be our answer choice. If you had done the math with this equation, you should come to the same conclusion. So if you want to verify it that way, go ahead. Alright, so that takes us to the end of a bunch of the example problems we have on the Bohr model. Any questions on those before I move on? Any concepts or parts of those problems that don't make sense at this point? Alright, if not, we're gonna plug forward and talk about now some of the problems with the Bohr model. So the Bohr model, it works great for hydrogen. It correctly predicts energy levels. It correctly predicts photon energies and wavelengths, the frequencies that are involved in these different transitions. We didn't talk about this aspect of it, but it also correctly predicts the size of the hydrogen atom, the radius, as it's often called. But it has some problems, and the biggest problem is with multi-electron atoms. So I already told you that the Bohr equation only works for one-electron atoms, and if you try to fit the Bohr model to multi-electron system, it just completely breaks down. It doesn't make those predictions correct at all. This is somewhat obvious because in multi-electron systems, in addition to having the attraction between the electron and the nucleus, you also have repulsions between the different electrons. So that, of course, is going to influence their energy levels. But even if you account for that, the Bohr model, even in no modified form, works. One modification that people tried was to do elliptical orbits. So the Bohr model assumes that the orbits are completely circular. Some people say, well, what if instead, especially in multi-electron atoms, you had elliptical orbits? Remember, an ellipse is just like a stretched circle, not completely circular, but still a round orbit. So they tried to do this, and all these math wizards went after the problem and tried to come up with models that account for elliptical orbits and see if that fits the data, and it still doesn't work. So elliptical orbits was not the answer. So this is one thing that people try, but adapting the model to include these elliptical orbits instead of circular orbits, as the initial Bohr model suggested, that didn't help at all. What is the notification that I just got? Alright, so if you include elliptical orbits, they did not improve the model in any significant way. So the reality of the situation is that the Bohr model only works for one electron systems, and only really works for predicting energy levels, and not a whole lot else, and radius, I guess, to some extent. But you can't use the Bohr model for anything that has more than one electron. That's a pretty severe limitation, because just about everything has more than one electron. And the other thing is that even though the Bohr model is quantitatively accurate, so at the very beginning of this section we introduced the hydrogen line spectrum, and the Bohr model reproduces the line spectrum of hydrogen perfectly, it reproduces the energy levels perfectly, but it's not a physically correct description. So it's mathematically correct, it works mathematically, but it doesn't really depict the real physical situation. So even in hydrogen, even when the Bohr model works, the reality is that electrons do not move in circular orbits. So this nice simple planetary model, as it often is called, with electrons moving in nice circular orbits around the nucleus, that's just simply not reality. Alright, so this model doesn't work for the vast majority of atoms and elements, and it's not even physically accurate anyway. So there had to be a new model that came out that could really address these limitations. So the model that came out is the quantum mechanical model of the atom, which is given by the Schrodinger equation. Now this is mathematically very intense, so we're not going to give you really the full mathematical forms of any of these things. The nice thing is, as we'll see very soon, is we can break it down again into just a series of integers that tells us everything we need to know. The equations, though, are, even if you had taken calculus 3, let's say, you'd still be probably a little bit behind mathematically on what you need to know to really fully appreciate the Schrodinger equation and all these different aspects of it. But we'll just give you the basics and ask you to at least know a little bit about them just conceptually. So the equation looks like this. Now, if you have taken more advanced math courses, occasionally I get math majors in here, or people that are just really far ahead in their math sequence. What this equation, it almost looks like, well, duh, H is just equal to E. What's so special about that? But it's a calculus sort of thing where this is an operator with this little hat here, this little caret above it means it's an operator, and then E is what we call an eigenvalue. So if you've heard those terms before, operator, eigenvalue, that's what these are. But again, we're not going to cover those details in this class. But this H here, what it stands for is, it's called the Hamiltonian. It's an operator. And what an operator is just a series of mathematical operations. Typically, many of them involving calculus, like derivatives and integrals and things like that in most situations. So the Hamiltonian is a series of mathematical operations. And when you apply them to psi, so this Greek letter here that looks like a little pitchfork is called psi. And we're going to define what that is here in a second. So psi, this Greek letter here, which we'll call the wave function, is also a mathematical equation. So you're basically applying a set of operations on an equation. So h is a set of operations, again, usually involving calculus things like derivatives and integrals. Psi is another mathematical equation that we're going to talk about here in a second. But when you apply the Hamiltonian to psi, you get what's called an eigenvalue, which is one of the allowed energy states. Which is given by E in this equation. E still means energy here. So the idea is that just like in the hydrogen atom, the energy levels are quantized, they're not continuous, you only have discrete allowed values for energy, and this much more complicated equation will allow you to extract what those energy levels are. Now, as I said, it's mathematically extremely complex, even for, even a 2-electron system is pretty nightmarish, and when you go to, real atoms and molecules that have dozens of electrons, it becomes quite laborious. So, this equation here, there's really not anybody that's doing this by hand and calculating things on pencil and paper for complicated systems. You're going to use supercomputers and software to help you do all this stuff. So it's, again, mathematically very complex, but it allows us to extract out these energy levels E. And the other important part of this equation that we're going to spend the rest of today talking about is this psi part here, which we call a wave function. And now we can hopefully see the reason why I introduced wave-particle duality last time, the idea that waves and matter have both particulate and wave-like property, because here we're going to really describe the electron as a wave equation. So it's not really a circular orbit or a simple path like that, but it's actually a standing wave. So psi is a wave function which describes the electron as a standing wave. And it's written typically in terms of, it can be written in terms of x, y, and z coordinates. That's a convenient way to think about it. So basically you put for atoms, you put the nucleus at the center, at the origin, and then you have a mathematical equation psi in terms of x, y, and z that describes a standing wave for the electron. Often it's also done in polar coordinates, where you're talking about the radius from the nucleus as well as the angular component. That's another common way of doing it. But it's a mathematical equation that describes the electron. And then another important point is that each energy level is associated with its own wave function. All right, stop writing here for a second. There we go. Each energy level has its own wave function psi. All right, so if you have a multi-electron system and you have multiple energy levels present, you're going to have, again, a wave function for each of those. So, and those wave functions, as we're going to see, are parameterized in terms of simple integers that allows us to easily categorize them and say some things about them without looking at the full beastly mathematical equation that they actually are. All right, so that's the Schrodinger equation. Now, an important part about this quantum mechanical model, which is described by the Schrodinger equation, is that we're no longer going to be thinking of electrons as moving in discrete paths or being able to easily say exactly where the electron is at any point in time. This is more of a probabilistic model, which can tell you where the electron is probable or likely to be found, but not exactly where it is. And the reason for that is from what's called the Heisenberg uncertainty principles. This is another one of those modern physics sort of concepts that came out around the turn of the 20th century. We're not going to do anything mathematically with this, but I want us to understand it a little bit because it helps explain why the Schrodinger equation can't give us the exact position of an electron, but rather is a probability type model. So the equation here is that delta x times delta mass times velocity mv has to be greater than or equal to h, which is still Planck's constant, divided by 4 pi. You can also write a form of this equation in terms of the kinetic energy, but here I'm writing it in terms of momentum, which is mass times velocity. So delta x is the uncertainty in position. In other words, how clearly do we know where that particle is at any given time? So it's an uncertainty in position. Do we know it's exactly here? Is there some range of values that are possible? That's what we mean by uncertainty. M is the mass of whatever particle we're looking at, and then delta V is the uncertainty and the speed of that particle. All right, so we should be comfortable with the idea that electrons are moving around the nucleus in some fashion. They're not going to be circular orbits anymore, but there is motion of electrons. They're not stationary. And so if we know something about the position of the electron, we have some uncertainty in terms of how fast it's moving, or alternatively, if we know how fast the electron is moving, there's going to be some inherent uncertainty into where it is at any given time. Now again, for macroscopic objects, this doesn't matter. So what this equation tells us is that, let's get to that in a second, but what the equation tells us is that it's impossible to know simultaneously no, I left a word out. The position and momentum of a particle, or alternatively the velocity, because if you know the mass, then it's really the uncertainty and velocity that you're dealing with for this delta mv term. Alright, so it's the idea that you can't precisely know both of these at the same time. If we know how fast the electron is moving, we can't know where it is. In real life, this doesn't really matter. So remember that h here is a tiny number. So in the analogy I gave in last class, I talked about throwing a baseball to the back of the room, which I think I could still do at this advanced age. But anyway, I talked about, if we're measuring a baseball moving through the classroom, and in that case it was in the context of the de Broglie wavelength and saying how, well, the de Broglie wavelength of that is going to be extremely tiny compared to the size of the baseball. And similarly, these uncertainties are going to be very tiny because they're dictated by this Planck's constant h. So for a macroscopic object, sure, I can know pretty precisely how fast it's going and its position. If I know that I threw the baseball exactly 70 miles an hour, and whatever that is in meters per second, I could measure its position x, and there would be an uncertainty given by this uncertainty relationship, but it would be, maybe like 10 to the minus 18 nanometer, or 10 to the minus 18 meters, something extremely tiny compared to the size of the object itself. So for a regular sized object, the uncertainty that we get, either in terms of position or velocity, is extremely tiny compared to the object itself, so it doesn't really factor in. But again, when we're talking about really, really tiny things like electrons, subatomic particles, this becomes significant, as I'll show you on the next slide. So this equation really only matters for small objects like electrons. So it doesn't factor into our everyday life. This isn't to say that we can't do accurate physics on large objects, but for very small objects, there's these limitations that are built in. And it's an important part of the quantum mechanical model, which again states that we cannot precisely know where the electron is at any given time, and that's related to this uncertainty relationship. So let's see how it works for an electron then. Just again, we're not going to do calculations with this equation in the homework, but I want to show you one demonstration here just to give you an idea. So if we have an electron moving at 1.0 plus or minus 0.1 times 10 to the 6 meters per second. Now I sort of randomly chose this velocity, but I think it is a reasonable amount of speed for an electron to have, so it's not an unreasonable number. And we want to know if that's the speed of the electron, what is the uncertainty in its position? And I gave you the mass of the electron here, which we talked about a little bit last time. Alright, so this is the situation here. This plus and minus 0.1 is the uncertainty in the speeds. That means that when we write it like this, the real speed of this electron is somewhere between 0.9 and 1.1. Alright, remember, anytime you do a measurement, there's some inherent uncertainty. You've probably talked about that more in the lab portion of this class. But this is the uncertainty for this measurement. We want to know if that's the uncertainty of our velocity, what is the uncertainty for the position as we try to measure it simultaneously. So from this Heisenberg uncertainty relationship, which we can write as delta x times m delta v has to be greater than or equal to h over 4 pi. Delta v is given to us here. It's this uncertainty in velocity, which is 0.1 times 10 to the 6 meters per second, or conventionally written as 1.0 times 10 to the 5th. So that's the uncertainty in our velocity, sort of the range of values that it could be is somewhere in that 1.0 times 10 to the 5th. And then if we solve for delta x, which is our uncertainty in position, that has to be greater than or equal to h over 4 pi times m delta v. Alright, so that's going to be rearranging this inequality to solve for the uncertainty in position delta x. And so we'll just plug in the numbers. Again, you're not going to do this on the homework, but I'm going to do it just to demonstrate real quick and see the number that comes out at the end, which is the important part. Alright, so we put all these in. Pi is the same pi that you've used in geometry class your whole life, or trigonometry. And then we have the mass of the electron, which is 9.11 times 10 to the minus 31 kilograms. And the uncertainty delta V, as we said, is 1 times 10 to the 5th meters per second. And the number that comes out of this is 5.8 times 10 to the minus 10, which is 0.58 nanometers. Now that might sound like a small number. You're like, oh, 0.58 nanometers, that's nothing. And yes, in your existence it is nothing. But if we think about, let's say, a hydrogen atom, like we've been talking about a lot today, this value here, 0.58 nanometers, is 10 times larger than the hydrogen atom. So if this electron was moving at 1 times 10 to the 6 meters per second and is bound to a hydrogen nucleus, in reality we have no idea where it actually is. The uncertainty in the distance or the position is 10 times larger than the atom itself. So this, I hope, demonstrates the concept that if we have really tiny objects like electrons that have masses on the order of 10 to the minus 31 kilograms, we cannot know precisely where it is. Okay? So we don't have to, again, don't worry about the details of this calculation, but the point is this quantum mechanical model tells us that we can't know exactly where it is at a given time. Alright, so before we start talking about this in more detail, let's get some more definitions out of the way. And what really does this equation tell us, or what do we have to know about it? Yes? This is a 4 pi. Yeah. Yeah, so it's a 4 pi. So again, you can verify that I did the math right, but the math is not terribly important for this concept. Now let's get into more definitions. So an orbital is, and often in many cases, in a mathematical sense, is a synonym for wave function. So each of those wave functions, as we said, is an equation for the electron, and it's going to be often referred to as an orbital. Now, in a colloquial sense, or at least in the way that we talk about it in chemistry, when we say orbital, we're typically talking about the region in space that the electron resides in. So what this wave function will give us, as we're going to work to, is a region of space where the electron is most likely to be found, and that's usually what we mean by when we say orbital. It's that region of space which is given by some geometric shape that allows us to have an idea at least of where the electron is likely to be, even though, as we saw, we can't precisely know where it is at any given time. So it allows us, this wave function allows us, in what we call an orbital, to determine the probability of finding an electron. In a given position. So we can't know exactly where it is, but we know what its probability is of being there, and then we can define a region in space where it is likely to be found, let's say 90% of the time is how we typically do it. So that's what we mean by orbital. It's a region of space, and it's dictated by probability of finding the electron there, although we don't know exactly where the electron is at any given time. Probability density, then, how does this relate then to the Schrodinger equation? Probability density is given by psi squared. So if we square the wave function, that gives us a function that tells us the probability of finding the electron, again in terms of x, y, and z coordinates is how we often think about it in chemistry. So it's the probability of finding an electron at a specific point in space. So this would be, you would take any random x, y, and z coordinate, you would plug it into psi squared, the square of the wave function, and that would give you the probability value at that exact location in space. Now that's not often a very useful way of thinking about things, because we're not usually interested in where exactly is the electron at any given time, or what's the probability of it being there, as we can find from this probability density. What we're usually more interested in is how far away from the nucleus is the electron. How likely is it to be that distance from the nucleus? And that's what the radial probability density gives us. So if we take psi squared and we multiply it by 4 pi r squared, where r is the distance from the nucleus that we're interested in, this gives us the probability of finding the electron at that radius. So this is usually what we're more interested in for chemistry, because we still, in some sense, think of electrons as sort of surrounding the nucleus. And what's more important to us is how far away are those electrons from the nucleus, as opposed to where exactly are they in space. So if we take our psi squared and we multiply it by 4 pi r squared, where r here is the radius that we're interested in and want to know what's the probability of finding it at that distance or that radius, that will give us the radial probability density, which is a more useful parameter for us. All right, so let's look at some graphs and then how these look for the ground state hydrogen atom. We'll have more of these plots next time when we talk about other types of orbitals. But the one that we have for the ground state hydrogen atom has this form here. So what's a little bit counterintuitive, and will hopefully make sense here as I explain it more, is if we look at the probability density, which is psi squared, so that's going to be on our y-axis is psi squared. I'll write that bigger since that font is kind of small. So psi squared on the y-axis, and then r on the x-axis. If we just look at psi squared, which again is the probability of finding it at any one position in space at that radius, not the whole radius together, what we get is actually a function that just monotonically decreases. All right, so it decreases with radius. And it never goes to 0. Now that's a little bit weird to think about, right? The probability of finding the electron at some distance from the nucleus never goes to 0. So if I have a hydrogen atom at the front of the room here, there is a non-zero probability that the electron is going to be at the back of the room. Now obviously that probability is going to be exceedingly tiny, but it is non-zero. So it approaches the origin asymptotically, if you like that terminology, but it never actually gets to 0. There's never a region in space where the probability is actually equal to 0. Although at some distance it becomes very small. Now the other weird thing about this probability density is that, well, wait a minute, the probability goes up and up and up as you get closer to the nucleus. Does that mean the electron is likely to be right next to the nucleus? And that's not true either, because remember that this is for just one specific point in space, and as you get really, really close to the nucleus, you have a very small region of space you're talking about, or very few points in space that are in that region. So again, the more physically realistic one is the radial probability density, which is the probability of finding it at a certain distance from the nucleus. All right, so what that's going to look like for hydrogen is you're going to multiply again 4 pi r squared psi squared. I'm trying to write that bigger so you can see it better, because I know this is kind of small. So 4 pi r squared psi squared. And in this case you have two competing functions. As you get farther and farther away from the nucleus, 4 pi r squared, the region in space that the electron would be allowed to be at that radius, gets larger and larger, but psi squared, as we see here, gets smaller and smaller. So they're two competing functions that move in different directions, and so when you multiply them together, you get a peak. Okay, you get a maximum, and then again, as you go to longer and longer radius, it still tails to 0. All right? So you're going to have this type of function here for radial probability density, which means that there is some value of the radius given here at the peak as we extrapolate down to the x-axis where the electron is most likely to be found. Again, we don't know that it's exactly going to be there. It's not going in a circular orbit as we talked about, but that's the radius, the distance from the nucleus where it's most likely to be at any given time. And this is what's called the most probable radius. And just to give you an idea, what this is for the hydrogen atom is 0.529 angstroms. Angstrom is 10 to the minus 10 meters, so it's as I said, about 10 times smaller than that last one we did. But this is the most probable radius for a ground state hydrogen atom. Alright, and so again, what the value of this function here means, this 4 pi r squared psi squared, is if we have our nucleus at the center here, and we have a bunch of radii drawn around it, concentric from the nucleus, 4 pi r squared psi squared is going to be the probability of finding it anywhere at that particular radius. So if we pick, let's say this 1, 2, 3, fourth one here, 4 pi r squared psi squared will give you the probability of finding it somewhere on this concentric circle with that radius from the nucleus. It doesn't say exactly where it would be, but it's somewhere on that radius will give you the probability. Whereas psi squared will just give you the probability of finding it at, like, boom, that point in space, right? But not the whole distance from that nucleus. So again, 4 pi r squared psi squared, the radial probability density here on the right, is more useful. Now the other way that we often think about orbitals is, as I said, it's not really practical or useful to think about, well, what's the probability at exactly that radius or exactly that radius? What we're usually interested in is what's the probability of finding it in some region of space at some distance from the nucleus, and we usually define that as the 90% probability region. So if we sort of, shade the area under this curve where we get to about 90% of the total area shaded, I'm just going to guess here, we call this the 90% probability region, assuming that I shaded exactly 90%, which I probably didn't. But the area under that curve, it's 90% probability region. And this would have then both a distance associated with it, what distance is the electron going to be 90% of the time, as well as a shape. So this, we haven't talked about the angular part yet. The orbitals can have different shapes as well. However, for hydrogen atom, it's just a sphere. And we'll talk about more why that is next time. But hydrogen atom has a sphere of some radius where the electron is going to be 90% of the time. The most probable radius within that sphere is this 0.529 angstroms, but there is a non-zero probability of finding it either closer to the nucleus or further away at any given point in time. So again, it's a probability model that tells you where the electron could be or how likely it is to be there, but not exactly where it is. Alright, so that's what we mean by probability distribution, radial probability. We're going to talk about these more next time when we talk about the shapes of orbitals. The only one we're going to really see now is the hydrogen atom ground state, where the orbital is a sphere. That region of space that the electron is likely to be in is just a sphere with some given radius. Now what we're going to close up today with is a discussion of quantum numbers. So we don't want to have to think about the full mathematical forms of these wave functions, because as I said, they're terribly complicated. We don't even want to necessarily have to think about probability distributions all the time. It's an important concept to know, but it's not the way that we usually think about things in chemistry. But what we really want to talk about is how do we break this down into simpler terms and parameterize these functions in a lot easier way and get some important information about the shape of the orbital, and then later on how that orbital is going to be involved in forming chemical bonds, which comes in Chapter 3. So what we're going to introduce now are quantum numbers. So we saw that the Bohr model does have a quantum number associated with it, n, which is that energy value 1, 2, 3, 4, and so on, that describes the energy level. For multi-electron systems, we have additional quantum numbers as well that are also part of the wave function. All right, so these are a series of integers. There is one that's not an integer that we'll talk about next time. That one's stupidly simple. But for now, we're just talking about orbitals, which are regions in space where the electron can be found. And these integers are part of the wave function psi. Alright, so psi is a very complicated function, but it has parameters that are given by integers that differentiate the different versions of psi that you have for the different types of orbitals. So these are those integers are called the quantum numbers, and they describe, and if we know what these quantum numbers are without even considering the full wave function psi, we can describe the energy, shape, and orientation of the orbital. Alright, so quantum numbers are a series of integers that are part of the wave function psi. They're part of that longer equation, and they describe the energy, shape, and orientation of the orbital. So if you know the quantum numbers for an orbital, you know those three things about the orbital, at least in a relative sense. For the ground state hydrogen, shape and orientation are pretty simple. Shape is a sphere. Sphere can only have one orientation. But for other orbitals, they have directionality. They're going to be pointing in the x, y, and z direction, for example. And one of the quantum numbers will tell us that. So let's see what those are. The first quantum number is still called n. So this has very close analogy to the Bohr model. As we'll see, it's really the same thing. It's an integer value, 1, 2, 3, 4, and so on. And we call this the principal quantum number, or sometimes the first quantum number. So this is, again, there's sort of a hierarchy here. This is the first one we always list, the principal quantum number. And now what is it related to? It's related to the energy and size of the orbital. And that, again, is very analogous to the Bohr model. Higher value of n tells us that we're at a higher energy level and that we're farther away. But again, it doesn't tell us exactly the distance. It just tells us that the most probable distance gets farther and farther away as the value of n gets larger and larger. But it does relate to the distance of the electron from the nucleus still, and its energy. And what this is often referred to is the shell number. So n equals 1 is the first shell, n equals 2 is the second shell, n equals 3 is the third shell. You may have seen that terminology before in other chemistry courses you've taken. Alright, so that's what n is, and it has a very similar meaning to what we saw in the Bohr model, or almost an identical meaning. But then the additional quantum numbers that we need, the second one is L, which is often written as a script L, like a cursive L. And what are the allowed values? So the allowed values of L depend on the value of n. So what shell are you in? So the biggest value of L is going to be n minus 1, and the smallest value is going to be 0. So L starts at 0, and then whichever value of n you have for that orbital, the biggest value of L that's possible is going to be n minus 1. All integer values are allowed, though. So it goes from 0 to n minus 1. It's still an integer value. So for a given value of n, you have 0 all the way up to n minus 1, and every integer value in between would be an allowed value of L. Now, this is referred to as the angular momentum quantum number. So from a strict physics standpoint, this tells you the angular momentum of the electron that's in that orbital. And what does it give us in a more physical sense that we can appreciate? It's the shape of the orbital. So knowing the value of L tells you what the shape of the orbital is. In other words, is that 90% probability region still a sphere, or is it some other more complicated shape, as we'll see for some values of L? And it also is involved, it contributes to the energy level if you have more than one electron. So the Bohr model works for one electron systems, and for that you only need the value of n to tell you the energy. That's what the Bohr equation tells us that we were working with earlier today. But when you get to multi-electron systems, it's the value of n and the value of L that dictate the energy of that electron. It's those two together, not just one or the other. Okay? So that's the difference between single electron systems where you only need n, and multi-electron systems where you need n and L to tell you the energy. L also then tells you the shape of the orbital as well. The last one then is m sub L. So it's m with a subscript L. And the allowed values of m sub L are, the biggest value would be L itself, and the smallest value is negative L. So this is the only one that can be also negative and positive. And it also includes 0, so you don't skip 0. So it's all values between negative L and positive L, all integer values, positive or negative. What we call this is the magnetic quantum number. That's what the M stands for. Rigorously speaking, it refers to the z direction of the angular momentum, but we don't have to worry about that because what it talks about from a chemistry standpoint is the orientation of the orbital. Because orbitals that are not spherical can be pointing in either the x, y, z direction or somewhere in between, and this m sub L then relates to that. There's not really a direct correlation, as we'll see, where a specific value of m sub L refers to a specific orientation, but it tells you how many orientations of that orbital you have, and each m sub L value refers to one of those unique orientations. Alright, so let's continue on then with some other definitions and considerations about quantum numbers. So if we have now 3 quantum numbers that designate an orbital. If you go to the second quantum number L, this tells you what type of orbital you have, and a pair of the first 2 quantum numbers, N and L together, is referred to as a subshell. Or a sublevel sometimes. Alright, so again, the allowed values of L start with 0, and then depending on the value of N that you're talking about, they go up to all other integer values. And usually when we're talking about sublevels, we don't use the actual numerical value of L. Yet we use a letter to replace that. So if L equals 0, we call this an S sublevel, or an S orbital if we're talking about a single orbital in that sublevel. If L equals 1, we call those p orbitals, which are p subshells would have a collection of p orbitals. And then this is going to be D. So if you know the value of L, you know what type of orbital you have, S, P, D, F, and so on. S, P, D, and F have sort of obscure origins, so don't ask me why they come in that order. It has something to do with studying the atomic line spectra that we talked about and some abbreviations they gave for them. But then beyond F, they more or less go alphabetical. So you go G, H, and so on. I think they skip L because it gets confusing if you have an L quantum number equal to L, but all the other letters just come alphabetically. We're not really going to see most of them because it's really only these 4, S, P, D, and F, that we're going to see in atomic ground states. So all the elements on the periodic table in their ground state, you're never going to populate an orbital that's beyond F. Alright, but again, to be clear about the terminology, if you have an NL pair, that's referred to a subshell, so you could have, for example, a P subshell, and then each individual orbital would be called a P orbital if it's in that P subshell. Okay, so P, S, P, D, and F can be used to label subshells or individual orbitals. Again, for the individual orbital, we also then would need one more quantum number, which is M sub L. So then what we have then for these 3 quantum numbers is a hierarchy where N tells us the shell that we're in. L gives us the subshell if we have N and L together. And then M sub L refers to an individual orbital. So if we have the value of N being 1, 2, or 3, those are, for example, 3 allowed values of N. We could go higher and higher than that as well, 4, 5, 6, and so on. If N equals 1, the allowed values of L are going to be 0 up to N minus 1. So if N equals 1, the only subshell we have is going to be L equals 0. Because L can be equal to 0, N minus 1 is also 0, so that's the only allowed value of L we have. Alright, so this is kind of like a little bit of like almost like a puzzle. So if N equals 1, the only allowed value of L that we have would be 0, because it goes from 0 to N minus 1. And then for M sub L, it's going to be minus L all the way to plus L. And again, if L equals 0, negative 0 is 0, positive 0 is 0, so we only have one value of N sub L, which is 0. So this is the simplest case. If you're in the first shell, N equals 1, you have one subshell that has L equals 0, and you have one orbital in that subshell that has M sub L equals 0. Okay, so those are, again, the rules, the hierarchy, or the relationships between the 3 quantum numbers. Let's go to a slightly more interesting one, which is the N equals 2 shell. So in the N equals 2 shell, if we go down to the subshell, L, the allowed values of L are going to be starting with 0 and going to N minus 1. This time N is 2, so N minus 1 is 1. So now we have 2 allowed values for L in the second shell, 0 and 1. So in other words, the second shell now has 2 subshells, one with L equals 0, one with L equals 1. In the L equals 0 subshell, we still only have one allowed M sub L value. I can never decide if I want to draw arrows on these or not. I'll leave them out because I'll probably forget. Arrows don't really mean anything. They're just drawing connections between them. But if we go to the L equals 1 subshell, the allowed values of M sub L, we have negative L to plus L. So we can go from minus 1, we include 0, and we can still have plus L, which is plus 1. And so what this means then is that the L equals 1 subshell has 3 individual orbitals, with M sub L equal minus 1, 0, and plus 1. And then finally, if we go to N equals 3, the last one I'll do, because these diagrams start to get ridiculous, n equals 3, the allowed values of L are going to be, I shouldn't draw the lines yet, let's space these out a little bit. We have 0, 1, and 2. Because again, the highest value of L is n minus 1. n minus 1 in this case would be 2 if n equals 3. So those are the allowed values of L. And then for the L equals 0, we still have just m sub L equals 0 is the only allowed value, negative L to plus L. L equals 1 has 3 allowed values of m sub L still, minus 1, 0, and plus 1. And then for L equals 2, the allowed values of m sub L, again, negative L to plus L. So L equals 2, that's going to be minus 2 to plus 2, and all values in between. So we're going to get 5 values. Make sure I have room for all these. I didn't draw this the greatest way, but you can hopefully see all these different values of m sub L. So in the L equals 2 subshell, you have 5 individual orbitals that go from m sub L equals minus 2 to plus 2 and every value in between. So these are the relationships between quantum numbers, and we'll just close with a couple of example problems of how we use this and some helpful relationships that come out of this. So the first one here is how many orbitals are in the third shell? How many subshells have principal quantum number n equals 3? I skipped one. So how many subshells have the principal number quantum number n equals 3? So remember that a subshell is defined by n and L together, the first two quantum numbers, n and L. So if n equals 3, we just did this in the previous slide, so those numbers are already there. L has how many allowed values? 0, 1, and 2. Remember, L goes from 0 to n minus 1. So if n equals 3, the biggest value of L is 2, and you go on down to 0. So because there are 3 values of L that are allowed, that means you have 3 subshells with n equals 3. And if you want to remember this relationship, you don't necessarily have to memorize these relationships because they come out of all of these rules for quantum numbers, but if you wanted to remember it, in a given shell n, there are n subshells. So the first shell has 1 subshell, the second shell has 2 subshells, the third shell has 3 subshells, the fourth shell has 4, and so on. So you get that; those relationships are going to be true for any subshell, any shell, and you want to know how many subshells are in that. The next one here is how many orbitals are in the third shell. And so here, if we're talking about orbitals and not subshells, you have to remember that an orbital is defined by 3 quantum numbers. N, L, and m sub L. If we go back to this chart that we drew for the third shell here, the number of orbitals is going to be the number of unique m sub L values that we have down here, or the number of, I guess, n, L, and m sub L together. So we just count this bottom row here. In the n equals 3, there's 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 orbitals, okay? So if n equals 3, we have 9 orbitals, and there ends up being a general relationship that for a given n, the number of orbitals is equal to n squared. All right? So we have n squared orbitals for a given value of n. So if n equals 3, we have 9 orbitals. And then did I do this other one? No, I haven't done this. All right, so that's a relationship that I think is helpful to remember because it gets a little bit tedious to write out all of the different ones. Let's do one more here just to close this out. I know it's a little bit late, but I just want to get to this one here, and then we'll save the last few examples for next time. Now we're talking about how many f orbitals are in a given f sublevel. So for a sublevel, it's going to be defined by n and L together. And if we want to know how many orbitals have that n and L value, all we need to know is the value of L. So for a given L, the number of orbitals is just given by 2L plus 1. Where that comes from is, again, if L equals 3, the allowed values of M sub L are minus 3, minus 2, minus 1, 0, 1, 2, 3. That's 7 values, or 2L plus 1. So if you're in the F sublevel, you have to remember L equals 0, 1, 2, 3. This is S, P, D, F. So that means L equals 3. And so 2L plus 1 equals 2 times 3 plus 1 equals 7. So like any F sublevel, whether it's 4F, 5F, 6F, any F sublevel is going to have 7 F orbitals in it. All right, so these relationships are going to be helpful, and we'll see them later on when we start counting the individual electrons as well. And we'll have a few more examples next time before moving on to new things.